Hello, thanks for being here. I'll be talking about where's the RISC-V vector ISA, what's the update. We gave an update last November, and we've been busily advancing, but let's get it out of the way. No, it's not ready yet, really getting close, but we've made a bunch of changes since the since the deep dive in November. We got a lot of feedback from people. The working group got a lot of members. That was really good, and we get quite a few active members. So between one thing or the other, we've been making some important changes. And the list is basically here. Fundamentally, we presented in November that we were going to have register types associated to each vector register, and we're making that an extension. There was a lot of feedback on too much state, concerns about saving and restoring, and although it gives us register types, really gave us a really nice encoding solution, we've gone back to a more classical encoding solution with all its problems to cram into the very busy RISC-V encoding space, but we think we're going to have a solution. A couple new things that have shown up: widening multiplies. I have a slide for it. We do have a heated debate on reductions. We've worked hard on overlaying the VREGs and the EVREG, and we've given up on it. I'll talk a little about vclip, support for speculative, and we now see a way maybe to have integer multiply adds, which back in November, January, we just saw no way really how to encode that. So let's go through these updates one by one. Okay, the big one is that the register types, and I apologize, you had to come to the tutorial yesterday to learn about the ISA. This is going to be really feature focused, but those of you that have been following the vector spec will understand. We said before that for every register we would have a type next to it, a few bits, and the type would set, hey, this register contains floating 32 or integer 16 or whatever. This is now going to move to an extension. So the base ISA, if you just want to build the most basic vector ISA, will be a classic ISA where the opcode tells you the type of the things you're working on. So very classic. The register type extension is there and will be used to provide the matrix operations that we wanted to get in. So that will stay there. And we will put with that the polymorphic encodings that we wanted to have on the current ISA, right? So, but as a consequence of this change, basically the vector instruction set is looking back, looks back to as a classical types, and I'll bore you with all the instruction mnemonics that we have, and we're now almost ready to say that we can encode everything within the existing space. We're not 100% sure, but getting there. We do have scalar support. One thing that the register type extension gave us was a very nice scalar support, so mixing scalars and vectors and having scalars of a large size. That was really nice. And so we've retrofitted that into the current encoding. We are, as a consequence, reducing the mask encoding to 1 bit, which will change a few things. And also the configuration is a little bit simpler than it used to be. I gave you some slides at the previous workshop, and I encourage you to go to that video and presentation on all the configurations you could do, or you can still do that, but actually setting it up is simpler now. So let's go to the big change in register types. So the basic thing, one consequence is scalar support. Before we could just say with the type, hey, vector v13, which is register 13, contains a scalar. That was really nice. And now we're going to do it slightly differently. Basically, what you'll be able to say is you'll be able to do a vector operation and say, by the way, the result is scalar. So the whole vector should contain exactly the same value. And there's a little semantic interesting detail there where the whole vector from 0 to max VL, remember the max VL is the maximum vector length, will contain one value that you've computed out of element 0 of the source 1 and source 2 registers. And to complement that, we've added, for vector loads, to go with it, we've added this new mnemonic VLO. We were looking for letters the other day with Christy and couldn't find any letter. And we ended up with vector load 1 element. We tried VLE, but that was aliased, and VLS, anyway, VLO. So essentially that allows you to, although you're working with vectors, you can load exactly one element from memory and splat it or broadcast it over the whole vector. And the two things combined, we salvage scalar support, so we still have scalar support within a more classical encoding. Okay, masked execution, also a change from November. We used to have 2 bits in the encoding, very expensive and very nice, that allow us to say, this operation is scalar, this operation is vector but non-masked, this operation is vector but masked under 1s or masked under 0s. We've lost that and we're back to 1 bit, so you're basically back to basics. You're either unmasked, that's it, or masked, and you use the LSB of V0 of I. If that's 1, that's your mask indicator. So, pretty much the same support as before, but we're back to 1 bit. So with those changes, the high level of what happened between November and today, what does the architecture look like? The picture is almost the same as in November. So we have 32 registers, that's your architectural state. Those registers contain a number of elements, and this is still configurable. So the same thing we explained in November. You, the software guy, the programmer says, okay, I want to work for my program, for my loop, or for my region of code, I need 16 registers, and I'm gonna, and the biggest element data I'm gonna work with is 32 bits. And you communicate that to hardware through the vconfig instruction, and hardware responds to you, say, oh, okay, you want 16 registers, 32 bit per blue box, and given the storage I happen to have here, this is the number of elements that I'm going to give you back. So that value there, max VL, that's the maximum value that you get from the hardware after configuring your vector unit. Obviously, any implementation will have a maximum storage. One company will have 8 kilobytes of storage for the register file, and that will obviously set an absolute maximum to the max VL value you'll ever see. But fundamentally, this thing is designed to be portable across different register file implementations. You can have 1 kilobyte storage, 2 kilobytes, 16 kilobytes, whatever you want, and this should be, your software will run on all of this. So this picture, the max VL is a little bit an implementation-dependent thing. You'll get the vectors of some length based on the storage that you have there. So no changes there. There are some changes coming on exactly how you specify how many registers you want. That's coming and will be in the spec very soon. But I won't talk about it today. And then in green, we have the new control state. No changes. The vector length register is still there, and it's still XLAN, and it still controls all operations that are vector. So no change there. And then regmax and emax with really say, hey, regmax, when you configure the machine, says, I only want to use 16 registers. So regmax is going to have the number 15, actually, 16 minus 1, or 31 for 32 registers, right? And Emax width is the element maximum width. You're saying on this region of code, I only want 32-bit objects, or 64-bit objects, or 16-bit objects, and the hardware should adapt, and good implementations will give you the most vector length possible with that thing. The rest type enabled, that's 1 bit. That's the bit ready there waiting for the type extension, and then the fixed point rounding mode and clipping mode, and we're adding 1 bit to FCSR that will take the saturation flag from the fixed point thing. So having said this, how is it looking today? Very recently coming. So let's start with vector memory instructions. So we got fundamentally 4 and 5 store vector load and vector store groups. Read first on the left. So we have the vector load 1, the thing that loads 1 element. Now, loads one element from memory and then splats the thing, broadcasts the thing across the whole vector. So it's still a vector operation. We have the real vector load, the normal one, the stride one load, the one that's most likely to be in your code. We have the strided vector load, and we have a gather, right? So these are the 4 fundamental types. And same thing for stores, vector store, one element, vector store, store strided, the scatter, the opposite of gather, and an unordered version of scatter for those that want to get the extra performance and don't care. Somehow they know that the indices and their scatter are not repeated, so they don't care in what order the scatter is performed. Right? If you now read on the right, which is an alphabet soup of letter, you'll recognize the standard RISC-V types that you know: byte unsigned, half unsigned word, blah, blah, blah. And in this yellowish color, the floating point ones, including half. So floating point 16 is mandated by the base ISA spec. So if you build a vector unit, you do have to build float 16 support in it. There's no way out of it. Okay, so hopefully the naming, the 2 first letters come from the operation, and the rest is the type, so no big surprises. Someone might be wondering how come they have fewer stores than loads. The reason is when you're storing to memory, the distinction between signed and unsigned is irrelevant. You just take a bunch of bits and put it in memory. That's why the stores, luckily, there are fewer of them and somewhat easier to encode. No surprises for you, I hope, on vector integer. You should recognize all the opcodes that you know from the base RISC-V ISA. So for every RISC-V operation that you know in the base, there should be a vector one. Novelties would be in the middle there, the widening multiply. I do have a slide for it. And the clip, we added some support for fixed point. And based on the final encoding, we'll see if the compares, we have the full set or not. We'll get there, just small details there. So hopefully here, no surprises. People have read this faster than I can talk. So you guys are there. Widening multiplies. This is an addition that will allow you to say, look, I have this data in my 32-bit register, but I really want you to look at it, look only at the low, it's a 32-bit register, look at the low 16 bits and multiply the 16 bits. And a nice trick that Christy added was that actually don't look at the 16 bits, look at 17, so that 17 bit is the sign. That way we don't have to encode the full set of sign multiply, unsigned multiply. So take the 17 bits from VS1, take the 17 bits from VS2 at the bottom, multiply them, you get a larger result, and you take the bottom 32 bits of that thing and you put it in VD. So that's the widening multiplies. And we're discussing on the working group of a double widening, so take a quarter of the register and multiply, and that's going to go together with how we exactly encode multiply accumulate. So stay tuned for news on these slides. Also, fixed point support. Actually, this is not new, but I failed to talk about it on the November presentation. So just for those of you that are interested in fixed point, there's a lot of DSP people building their own vector units. So this is they should like this. There's basically one instruction, vclip. There's a type, byte unsigned, yada yada yada. Takes 2 registers, 2 vector registers. The second source tells you. The first source register is the data you want to clip. The second source is a shift amount, so you basically shift the data in the first register by that shift amount, shift right. Then you round according to that VX rounding mode that you see there, right? And after rounding, you apply the clipping, either saturate or wraparound. Some people call it modulo. They just, you basically ignore the top bits. So that's nice support for people doing fixed point. Moving on to floating point, I hope, again, absolutely no surprises here. Every instruction that you have in the base, S and D are here, and in addition, you are required to implement 16-bit floating point. That's the H data type that appears there. I do find the mnemonics highly aliased in RISC-V, but anyway, that's unfixable now. So really no surprises, mean, max, sign, divide, multiply, really no surprises here. Multiply, add, first we thought we're going to have the full set of multiply adds. The slide is a little bit outdated from our discussions, very recent discussions. We first thought we had to give up on the negate versions of the mul adds. It now seems we'll be able to encode everything that we have in the base. So we have a plan to actually support everything. And then the widening concept that we had for just a multiply also extends here. Now that's more interesting to the machine learning people because now they can see, I have, I can multiply two 16-bit things, add it to a 32-bit thing, and I get something that's valuable for me. So that will also go in there. So that's new. Converts, full set of converts. This is a, from integer to float, from float to the max integers that you have, from float to float, obviously all combinations, and from a large integer to a narrow integer. Again, it seems that we will be able to just encode the exact same mnemonics that you know and love, fconvert SW, fconvert SWU. That's really dependent a little bit on the final. Do we have every bit to encode everything? And so the names here do not sound familiar to those of you that know the converts. That I there is new, and that's our placeholder to say, well, if we cannot encode all of them, we'll just have this new naming. But hopefully this slide will disappear from your life and we'll go back to the base encoding. So that's how it's looking now. Data movement. Again, I don't think I presented this in November. So only those of you that followed probably are aware of this. So good things. Fundamental operations. You will be able to insert one piece of data into your vector. So that's the two inserts at the top. Take either a GPR or an FPR and stick it in the middle of your vector wherever you want. That's one operation. You can also do the reverse one, extract. You can take of your vector, any particular value, get it out, and put it in a GPR or an FPR. That's extract. You obviously we're going to have the classic vector-vector merge. Most people will know this by a conditional move operation. Basically, there's a mask bit for every element, and you select between the two sources, and you write that into the destination vector register. Additionally, you will be able to do a merge between a full vector and a single scalar, so you'll be able to blend in one scalar in the middle of your vector any way you want based on the mask, or a somewhat expensive operation. You could actually set the whole vector to one integer register by just setting the mask to all ones and doing a merge. That's a bit expensive, but you can do it. But to speed up that particular operation, we also have the splat. I had to look up in the dictionary that word. I'd never heard it before. But it's a broadcast. At least, if you know the x86 broadcast will sound more familiar to you. Basically takes one GPR or FPR and just copies over all vector. One particular detail of this operation that's a little bit unusual is that it ignores VL. So contradicting myself, I said everything obeys VL, so not this instruction. And that's done so that you really get the scalar behavior you want. When you're thinking, I want to multiply a vector by a scalar, right? And you're thinking my VL is 19, you do think that the vector register will be constrained by 19 through the VL. But the scalar is not as unconstrained. It's one scalar, right? By doing this, what you can do is you can completely fill up a vector with one value, and irrespective of the VL changes you do, you'll get that behavior that you wanted, right? So it's a way out of not really having types and not really having encodings. That's going to allow normal scalar behavior. And obviously, the smart implementers in the room are not really going to copy this value into every position in the vector. They'll just have a bit somewhere in the microarchitecture completely hidden that says, V19 contains a scalar. Next time someone uses V19, I'll just get it from this other flip-flop that I have here on the side and not really read the V19. But obviously, that's an implementation choice. You can just do the simple thing and just copy the value everywhere and be done with it. And then the final data movement, I went over register gather, super important operation. You will have a complete register to register gather, so you'll tell the hardware, hey, I want to move these elements to this other position. This will be it is a superset of other architectures, permute, and other, shuffle up, shuffle down, and all those nasty things. So you'll just get one operation. You'll be able to put anything you want in any other location of the register, of the vector register. Now, however, that's going to be somewhat expensive. It is possible that you can optimize, and that's why we have slide down and slide up. You can take a piece of a register and just move it all down. That's going to be really useful for reductions. And by providing this opcode, we hope that implementations will actually be a bit faster than a full register gather. So you'll have to use register gather when you really are completely randomly replacing, moving things around. But slide down and slide up should be a little bit better. Mask operations. Remember, I didn't say it, but remember from our November presentation, I'm sure you all read it last night before going to sleep. Remember that the mask is really just V0, so there's no special mask register. When you want to do a mask operation, when you do something under mask, you're using the LSB of every element of V0, right? So really, computing mask is nothing special. You do vector equal V5, V6 into V7. You can AND V7 and V8, blah, blah, blah. But there are a couple support operations that will allow to read that mask and pass it onto the scalar side of the world to do other kinds of computations that are very important. One, it's in the second position, but a very, very important one is to just count how many mask bits are set, because there are many programming styles that say, well, this is worth while I have at least 8 or 10 or 12 vector elements available in my lanes, but if I drop below 8, I want to just get exit and run this thing in scalar. People coming from the GPU world will recognize this kind of thinking. So that's pop count. We'll pop count your mask. VM first will, as the text you've already read, will find your first bit set in the mask. So you can know where you want to store something. IOTA is a very classic instruction that was available in a similar form in Cray, and basically counts and returns you in a vector how many preceding mask bits are set. And this is actually useful for histogram, for many things. And so it's somewhat expensive, but I think people are going to like it. And then a couple very cheap support for speculative vector execution. It's not going to cost you much, or even if you later decide not to do the speculative execution extension. But flag before first is going to give you a mask of ones up until the first bit set in the mask, and flag including first is going to give you that plus the first set bit in the mask. So then you can know, if you're thinking speculative vector execution, you can know, I've done all this work up until this point, I got more work to do or less work to do, or whatever you want to, whatever way you want to think about it. 7 minutes. Reductions, the standard set of reductions. We do have an ongoing debate on whether these should be in the base or not. The software people really would like them. Some of us in hardware that have built this and never really were happy with how fast they were. I think, no, we should just do it in software. So the debate is ongoing. Please join the working group and chime in if you want to have your way into the final spec. And encoding, not meant for you to read it, and it's small, but those of you in the first rows will recognize that we are pretty much fitting everything into the existing encoding space. So the loads are going to 0x7, the stores into 27, which was the store encoding. We've taken 2F, 43, so these are all normal encoding. So our goal really is to fit this whole thing into the existing opcodes and not take any major opcode. That would be really nice, and it's looking good. It's not finished, but looking really good. We have some troubles in 53, but I think we've figured out a way. We're very, very tight there, given the way the current encodings are, but we think we're going to fit. So it's looking good for 0 major opcodes and just fitting into the existing opcodes. And that's my last slide, doing better than I thought. we really are close to closing the base spec very soon. If we get the encoding done, I think then that's pretty much it. The integer multiply adds are probably the last thing to go in. And then Christy did do a long write-up, so we are pretty much underway. If you are in the mailing list, you got that write-up anyway, so you've seen it. We do want to see compiler output before bringing for ratification, so we obviously, it's our homework and our deliverable to have a frozen spec, then have the compiler people actually start moving and be able to generate code and say, oh my God, that was horrible. We're not capable of generating this kind of code. And we did say we would start on a formal version of the spec, but actually no work has happened. But we'll make promises again for next workshop, next summit actually. And we will try to have some starting there on the formal spec. So I think that's it.
On the vector slide, is there a limit on the index? Has it been less than or equal to the vector maximum length?
On the vector register
on the
gather?
vector slide, the offset, so when you copy...
Yes, it has to be less than, and if you go past, you get zeros.
Okay, thank you.
Yeah, and the whole ISA, I said it yesterday, I'll take the 3 minutes to repeat. The whole ISA contains zeros. Wherever there's a doubt, we generate a zero as a recognition that eventually someone will do an out-of-order implementation of this thing, and they will, hopefully they will thank us. Maybe we'll be old and retired by then, but someone will thank us.
How long do you think you're going to need to get feedback from the compiler people about before you could finalize the vector architecture?
I saw Alex. Where's Alex? He was here. I don't know. Well, you know, LLVM is probably you're the furthest along on a compiler support.
Robin, who's back there and is around the next few days, he's been looking at that, T-Darmstadt. I think a challenge has been that the vector ISA has been changing in various ways. The fundamental aspect, which is difficult to model in the compiler, which is the variable size register, registers, is there's some, again, Robin kicked off a discussion with the upstream community about how to handle that. So I hope we'll be able to reach some agreement there in the near future. It'll be dependent on people getting involved and getting stuck in. We've had some good discussions with people upstream, like the vPlan team at Intel, on supporting that with their vectorization model. But I've already spoken to a number of people here who are intending to work on vector extensions or interested in contributing. So doing that sooner rather than later is the best way to help push that forwards.
Thank you. So soon.
Hi. You were mentioning that you didn't want to take up a full major opcode, and I was wondering what kind of things do you feel that you're leaving out by not using up more encoding space? You mentioned the 2-bit mask having to go down to 1-bit. Are there more things that you would like to do if you took up more?
Well, we were discussing the other day probably the 2D encoding, so having a vector being seen as a matrix, which will require a double vector length support and double stride support to load a matrix from memory and stuff like that. Probably all of that might either take a major opcode or might go the type extension way. Unclear yet, but that would be probably a candidate for taking a major opcode to do the whole 2D, which is just adds more complexity, more types. Then you have two dimensions. You need more bits everywhere. So that's probably what would be used for, or at least we're saving for others. They're going to have bigger ideas. Yep.
So in your multiplication opcode, you basically talked about a 16 by 16 to a 32-bit result. Maybe did I miss a 32 by 32 to a 64?
It's going to be the same thing.
And 64
yeah.
64 by 64 to 128.
No, no, we don't have that because no, we don't have that. No.
Okay.
We're down at 0, so that's good. Yeah. Thank you.